was 10 years old, I used to live in Shepherd's Bush in West London. And every Saturday afternoon, I used to go to Shepherd's Bush Market. The reason I went to Shepherd's Bush Market because I was keen to see what people were selling, what they were buying, but most importantly, what they were throwing away. Because frequently among the rubbish, I could find something useful, e.g. wood with which I could make a cricket bat. However, every Saturday afternoon at Shepherd's Bush Market, there was a very strange man. He was selling medicines. He was selling medicines in a form of purple tablets. I've got some here to show you. And he told everyone these medicines could cure you of any problem which you could have. Whether you had muscle pain, toothache, neuralgia, nostalgia, you name it, this medicine could cure it. And he said the reason why his medicine was far better than any other medicine was because his medicine didn't contain any acid. And many other medicines contain acid, and everyone knows that acids burn. And he said he had some examples to show. He had some Seidlitz powders, for instance, which is used for stomach complaints. These contain tartaric acid. Acids burn. He had some Andrews liver salts, which contain citric acid. Acids burn. And then he had some aspirins, and he said, watch carefully because I have a demonstration with you. Look into the instructions on this. They contain acetyl salicylic acid. Acids burn. He said, watch carefully now while I do an experiment to show you the frightful effects that could occur with these horrendous substances which burn your stomach. He had a tin lid on Shepherd's Bush Market, and on the tin lid he had some crystals. On the crystals he put the aspirins, and then he said, when you have a sore toothache or a muscle pain, you may also have a sore throat, and you may therefore take some baby syrup, some syrup, cough syrup. He actually had some Sanatogen baby cough syrup. He poured that on, and he said, watch carefully because this dangerous mixture, and he sprinkled some water because you said you may also take a sip of water. He said, watch carefully because in the space of the next few minutes, you will see how this might actually start to burn in your stomach. And as he was talking, suddenly the whole thing erupted into flames. Everyone was absolutely horrified. How is it possible to have this horrendous medicine burning your stomach? And do you know what people did? Please excuse me, I'm just going to lob this into some water here to put the fire out. Do you know what people did? They put their hands in their pocket and they pulled out half a crown, which was a lot of money in those days, and they bought his medicine. However, I as a 10-year-old was very lucky because to start off with, I was never ill, but more importantly still, I had no money, so I couldn't buy it in any case. But I had been born with a serious psychological problem ever I had since I had become a very, very small baby. This was a secret, an obsession, an obsessive passion with fire. Now, my parents had bought me a chemistry set when I was 8 years old. I mixed all the chemicals together. All I could get was color changes, smells, smokes, and fizzes, but I couldn't get what this man was doing. Fire became the dream of my whole existence. And yet this man here at Shepherd's Bush Market selling medicines was making fire using medicine and water. So I decided I would try this experiment at home. I knew where I could get the aspirins, Boots the chemist in Uxbridge Road. I knew where I could get the water from the tap. I knew where I could get Sanatogen baby cough syrup, but I didn't know the identity of those strange crystals. So I decided to find out. I went along to Shepherd's Bush Library where I borrowed a book which was called Chemistry and Magic. And in that book I looked up all the possible ingredients, and there was one substance which seemed to fit the bill. It was called potassium permanganate. So I went along to Boots the chemist. I purchased 1 ounce of potassium permanganate, set this up in my mother's kitchen at 44 Stanley Road, Shepherd's Bush, London, W12, did the experiment, and the greatest day of my life occurred because the experiment was a success. The kitchen was filled with smoke, but that was a defining moment in my life because ever since that day, I have been conducting chemistry experiments, and it is the virtues of the science of chemistry that I have come to tell you about today. I'm going to argue the case for the importance and the brilliance of this subject. Now, chemistry is the science of substances and how they turn into different substances. And very frequently we can recognize a chemical change because there is a change of color. So we recognize the formation of a new substance by a color change. Now, chemistry is hugely important in today's life. As we all know, plastics, adhesives, cosmetics, medicines, fuels, agricultural chemicals, explosives, chemistry has played an enormous role in our science today. And I'm just showing you some examples of simple chemical changes because chemists are people who have learned to understand these changes and use them for our huge benefit. And here we see some chemical changes. Every time you see a color change, I am showing you a new substance being made. Therefore, we are observing a chemical change. I have shown you some simple reactions here. Now, here I have a water which popularly magicians like to call magic rainbow water because this water can show all the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet, as everyone knows. I squirt some of my magic water in, and here it is going. I can't guarantee these results because this is all a little bit of trial and error stuff, but here we go, etc. There we are, a little bit more. As I said, I really don't know, but it's a bit of hit and miss, you know. But here we go. We're sort of going our way through the spectrum of the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. We've been green, orange, yellow, green, early yellow, orange, and now perhaps we'll get to red. Let's try again, and now just add a little more. There we are. We have a nice red color continuing to add here, and as I said, I'm not quite sure where it's going to go, but as I said, this is important because this is illustrating every single color change is actually a new substance being made. No, it hasn't finished yet. It hasn't finished. There it goes. One can never predict, you see, the science of chemicals. Chemistry, even with chemists who know what they're doing, is sometimes unpredictable. But the most important point I'm trying to make today is we benefit from this on a huge extent, to an extent that we frequently don't even realize, you see. And here we are trying to get red, orange, yellow, green, blue. There's a blue, there's indigo, and finally violet. I'll just swirl it in, you see, and therefore, just to show you there, and I'm just going to swirl it in, and we've got purple. Now, you see, I've shown you some chemicals. No, I'm not here for applause. I'm here to instruct and educate. Now, ladies and gentlemen, I've just mixed some colors. See, you can't just mix any solutions together and get them to suddenly change color. And they say, because I'm making UK, because things don't happen like that. We have to supply energy. Chemical changes are always associated with energy. There are various forms of energy: heat energy, light energy, electrical energy, mechanical energy, kinetic energy, nuclear energy, all sorts of energy. This most peculiar experiment, though, is actually activated by musical energy. If you watch carefully while I play in the key of A major. And they were amazing, but this is the sound. No, I'm not here to collect applause for musical performances. As I said, I'm here merely to explain some of the amazing things about the science of chemistry. But I wanted to tell you something about the science of physics as well, because that's another one of the fields which I have been passionately interested in. And I wanted to introduce you to a liquid which is among magicians popularly known as magic disappearing water. And the reason why it's called magic disappearing water, because if you look at it carefully, then it does literally disappear into thin air. Now, no doubt many of you will recognize this, of course, is liquid nitrogen. It's air, main part of air, which has been cooled down to minus 196 degrees centigrade, has huge industrial use. But I just wanted to show you a couple of interesting effects which I've developed in this, and these involve the idea that when liquids boil, they expand hugely. So I'm going to pour some liquid nitrogen into some Sprite bottles, which are designed to carry a very, very high pressure, because Sprite contains carbon dioxide dissolved under high pressure. And I'm going to do the thing that you should never do, and that is to close them once the liquid nitrogen is inside and has reached a thermal equilibrium with the bottle and the surroundings. Now, the reason why I should never, ever close a liquid, and you see liquid nitrogen being at minus 196, boils at room temperature. We've got about 22 degrees centigrade in here, and as the liquid nitrogen is boiling, so it is generating gas. Now, a lot of people don't know that when liquids boil, they expand. The expansion coefficient of a liquid boiling is about 1,000. So what's happening is that liquid nitrogen is boiling away. It's going to generate an enormous pressure in the bottle. So I'm going to put the bottle inside a dustbin and leave it. It takes about 5 minutes. Now, if we're lucky, I'm just waiting for it to stabilize itself and stop boiling vigorously. And we're going to put the top on here very carefully. And I'm going to then put the lid on the dustbin. And then I'm going to put it on very tight. Now, what's happening is as the liquid nitrogen is boiling in there, it is slowly turning to a gas, and eventually it'll enable a pressure to be built up, which is so huge that the bottle will no longer be able to withstand the pressure. And when the bottle can no longer withstand the pressure, it will then explode. Now, I put it inside a dustbin. Sometimes it makes quite a loud noise, and I do have to warn you for that reason that this may be actually, you may actually get a bit of a shock, and the lid sometimes goes flying into the air. But I can reassure you we are merely illustrating the principles of physics, and which play such an important role in everyday life. So I'm demonstrating the expansion of a liquid when it turns into a gas. expansion under constant. So there it is, it's boiling away in there. I'm going to put this one in the smaller dustbin. Now, I do have to say these are hugely unpredictable, these reactions, and I'm quite terrified of doing them, but in the interest of science and education, I believe it is important that we should all witness together. We can only, the reason why I made so much progress in science and technology in the last 300 years, because we always see what we believe, and I'm very much hoping, believe what we see, should I say, and I'm very much hoping. Now, what happens, these lids sometimes fly off erratically, and it takes about 7 minutes. In the meantime, I wanted just to show a couple of features of liquid nitrogen. Being so cold, of course, it will freeze water, so I'm going to set up some liquid nitrogen here and freeze a tiny, we're waiting for that to go. It's sort of, it'll just go suddenly, so don't worry about it. You'll suddenly know it's happened when it's happened. It's unpredictable, but I think part of the fun of science is you can't always predict every effect. Now, I'm going to, sorry, I've dropped my top down there. I'm just going to bend down here to pick it up. Not that there's any other reason other than I like to be tidy. So we've got some here. I'm just going to pour some liquid nitrogen. I've got some more liquid nitrogen here. Now, this is water. This is interesting. Two colorless liquids together. Now, there I mix colorless liquids together, and I caused a chemical change. I was making a new substance. But here I'm causing a physical change. One of the liquids is turning to a solid, and the other is turning to a gas. The latent heat of vaporization of the liquid nitrogen is being exchanged for the latent heat of solidification of water. So the water will freeze and turn into a solid. Now, in the meantime, I'll just show you another experiment. We have some rubber tubing here, which is elastic. It's elastic because it's made of molecules which can actually store energy. You stretch them and then they go back to their shape. If you put them into liquid nitrogen, a piece of rubber tubing, it undergoes the most interesting change. The first thing is there you see a nice fountain of liquid nitrogen coming out. Now that fountain of liquid nitrogen, once again, is caused by the pressure of the liquid nitrogen, which is boiling in the tube, because the tube is very hot compared to the liquid nitrogen, and therefore it's forcing the liquid nitrogen out due to the pressure as it changes from a liquid to a gas. Now we'll leave that in there. It's now reaching thermal equilibrium, and by the way, the bottles might go off any second because I can hear them crackling inside. They don't always explode, by the way. They don't always explode, so I do have to warn you. Now, I'm just going to take this out, and you see now, from being an elastic solid, this has now become very brittle indeed, so brittle that it's broken into a small number of fragments. I'm going to just carry on adding water here, and I just wanted to show you one more interesting experiment, and that shows you the effect of pouring liquid nitrogen onto an inflated balloon. You see, the balloon here has a certain pressure because it's contained within an elastic membrane, and that elastic membrane is able to store the gas inside, and it's exerting a pressure because the molecules have a temperature and they're vibrating and moving rapidly. However, if we cool them down, they stop moving, or their movement is severely reduced, and therefore they exert a much lower pressure. And therefore what happens is the balloon therefore subsequently contracts, and you'll see it getting smaller and smaller here as I'm pouring liquid nitrogen over it. This once again demonstrating the remarkable change in the volume, the compressibility of gas with change of temperature, the change of volume of a gas with differing temperatures. So I've collapsed my balloon. Now this of course is an example of a physical change. I did say they are rather unpredictable. Now here, no, please, I'm continuing. And this is here, we now have our balloon here. We now have our balloon, and as I said, this was the physical change, so the balloon is now warming up. The molecules are gaining more energy. As they gain more energy, they exert a greater pressure, and so the balloon is restored to its previous shape. Now, having demonstrated that, I'm going to now move. No, please, ladies and gentlemen, I'm here now. I'm going to now talk about something that we all use on an everyday basis, on a very, very regular basis. All of us use lots of these every day. Now, I'm sure you all know, of course, because this is the piston of the inside of a motor car engine. Now, motor car engines are phenomenal inventions, but what I wanted to make the case for today, it's thanks to the science of chemistry that we have motor cars. You see, whereas the piston is a modern invention, the genius of the mechanical engineer, the metallurgist, and the physicist, the way the petrol burns is an invention of the chemist, or the discovery of the science of chemistry. I just wanted very quickly to illustrate this for you, and I think that bottle may be getting quite under high pressure in there, so do keep an eye on it. There it goes. That was the second bottle. So that too was success. No, please. I'm in a hurry. I'm in a hurry. I'm now dashing on, and I wanted just to show you, how motor car engines work. I wanted to start off by telling you that petrol, unlike the motor car, petrol is not a new invention. I have here a few droplets of petrol. I'm going to ignite the petrol on a asbestos mat, which I have here, and I'm going to show you how petrol burns. Petrol substances similar to petrol have been known to humans for thousands of years. Crude oil, which comes out of the ground, has been processed in a variety of ways by alchemists and technologists working here. Please watch carefully. This is our control experiment, a sample of petrol burning in the way it has been known to burn for thousands upon thousands of years. There's our candle, which is a mixture of hydrocarbons burning. Here is our splint burning, and now we set the petrol on fire. Now, the question I'm saying to you is, do you think this will make a car do 100 miles an hour down a motorway? The answer is clearly no. The flame is yellow and smoky. Hydrocarbons burning in air, limited air supply, incomplete combustion, excess carbon-generated smoke. Note the similarity of the flame. Wood burns with a similar color flame, and candle as well, because they are both rich. They are all rich in carbon. So that's how substances similar to petrol don't burn for thousands of years. However, I have here a model of the inside of the interior of a motor car engine. It's a tin can. And the genius of the motor car engine is that chemists had recognized the vital component of air which makes things burn better, the vital component which makes things burn better. Oh, by the way, in the meantime, our glass beaker has shattered. It's shattered as it froze. There are fragments of glass all over the place, and it's actually, there you are, oh dear. And this demonstrates for you the very high forces which are set up when water expands. It expands by hydrogen bonding, and that is the capacity to rupture all sorts of things, including car engines and so forth. So that's another example of a demonstration of the powerful physical effects of water turning into ice. Now, I have here the inside, a model which represents the inside of every single motor car engine that exists on this planet. And it's called a cylinder. All motor cars have cylinders. And inside the cylinders, they have pistons going up and down, which all of us have these, of course. And we know how they go up and down in linear reciprocating motion. And that is converted to rotary motion or rotating motion by being connected to the crankshaft. Now, the petrol burns inside the cylinder. And what I wanted to tell you, which was the genius of the chemist who actually got the petrol to burn this way. Allow me to demonstrate. This then is the model of the cylinder. Instead of a piston, I've got a tightly fitting lid. And instead of a spark plug, which is normally used in modern car engines today, I have a hole in the bottom where I'm going to put my flame. Now, I'm going to tell you, this is the clever thing. If I were to say to anyone, what's this tin got in it, you would be perfectly entitled to say it's got nothing in it, because it had paint in it, now has no paint in it. But from the point of view of combustion, and this is the genius of the chemist, it is full of a most important commodity, and that, of course, is air. And so I'm now going to pour in a small quantity of petrol, the same quantity that I had before, and I'm going to show you how differently it burns once it has gone into there. So please note, the amount of petrol is literally that much there. So I've just poured it in there. We now put the lid on very tightly. Petrol is highly flammable. It's therefore very dangerous. So we must make sure that any containers with it are carefully closed. I'm just going to put this lid on now as tightly as I can, just to make sure it goes around. And the petrol in here is now undergoing a most important physical change. It's not burning. There's no chemical change. But petrol, being a volatile liquid, is now evaporating. As it evaporates, and this is the genius of the chemist, it is forming a homogeneous system with air. It's mixing with the air, and therefore it is no longer in the form of a liquid. It is now in the form of a gas, which is thoroughly and completely mixed with the air. And this is what happens inside all internal combustion engines. They're called internal combustion engines because the fuel burns inside the air. Please watch carefully inside the cylinder. Please watch carefully. I'm going to now ignite it and see if you can spot the difference between the way the petrol burnt last time and the way it burns this time, and see whether you would agree that this could make a car do 100 miles an hour down the motorway. Please watch carefully. This doesn't always work. And there it is. The lid went flying up, and there it is. You see, no, I'm just demonstrating. I've almost finished. Just a couple of more experiments, just to show, because people don't realize how much it took thousands of years to discover all these wonderful facts about chemistry. Now, did you know, once they had discovered that air is a mixture of gases which contains oxygen and also contains nitrogen, people started experimenting with oxygen, the vital ingredient which makes things burn better. And they started trying to make things burn better by adding oxygen. Now, one of the experiments they did was they tried to add oxygen to cotton wool. Here is a piece of cotton wool burning, a cellulose, a naturally occurring polymer, a thoroughly burning combustion, boring combustion, because it's actually surrounded by 20% oxygen. However, in about 1850, two scientists working independently, Asconio Sobrero, an Italian, and Christian Schönbein, a German, managed to achieve effects with substances similar to cotton, cellulose, and glycerine, and they achieved a type of cotton to which they added extra oxygen. Now, this has been chemically combined with extra oxygen. Notice it's got the same color as cotton wool, but this cotton wool has a different mass. It weighs a different amount, and before it was nitrated, we used the technique of nitration, a mixture of concentrated nitric and sulfuric acid to add extra oxygen. Before it was nitrated, it weighed 1.7 grams. Now they weigh 2.8 grams each. Please watch carefully while I set this on fire and notice the difference in the presence of oxygen, extra oxygen has to the rate of combustion of the cotton wool. And there you see an instantaneous combustion. Now, what's that merely demonstrating is the achievement of the science of chemistry, improving the way fuels burn. Now, I've demonstrated for you what's actually a high explosive. It's called gun cotton or nitrocellulose. And I'm going to just very quickly show a short experiment in which I shall fire, hopefully, some ping pong balls into the ceiling. And what I've got for this purpose is a specially constructed mortar here. I have made a hole at the bottom there, and I have a gun cotton cage here. I'm going to quickly lob in a small quantity. Yeah, let's let the whole lot in. This is, by the way, can be, no, this is quite vicious. I'm very concerned with health and safety. I wouldn't want to have someone getting a shock or indeed, etc., some sort of trauma as a result of coming here. So I'm going to drop this inside here. Now, this is called a gun cotton cage. It's dropped inside. Please listen carefully. Et voila, it's gone inside. We now put in 1, 2, 3, 4 ping pong balls. We put it up here, and then we put underneath it, we put our asbestos mat, our mat here, and now we put a little fuse in, set it on fire, and just once again illustrated the principles, the wonderful achievements of the science of chemistry. And this, of course, is not only chemistry, it's pyrotechnics and a whole load of other things. And after this, I've got one more experiment to go, and I hope I've made my case about the importance of the science of chemistry in everyday life. Please excuse me, I'm just getting a tiny little bit of fuse. I need to set this off with a fuse which I have here, and I'm going to just take it out of my tube here. Now, the fuse is a conventional fuse which we can make using standard gunpowder. It's the sort of thing they use in fireworks. It's nothing that special. I'm going to pop it into here, and then I'm going to set fire to the fuse, and hopefully will stand back. There'll be a bit of smoke, there might be a bit of a bang, and hopefully the 4 ping pong balls will go flying somewhere into that. I try and direct them approximately there. They are genuinely very, very light, and I said I can't guarantee whether this will work, but then one must always experiment. Now, just let me double check that everything is secure. We wouldn't want to have a mishap here. Sometimes things go wrong. So please watch carefully. This is then gun cotton in action, acting as a means of projecting a propulsion rather than an explosion. The fuse is just about there. There it is, we're off the mark. Fingers, no, watch out. I hope it'll go bang. There we go. I'm sure the balls went somewhere. I don't know where they went. Now, are we okay? Is that fire? There's not catching fire or anything. Is that okay? Right. Thank you. But that was that then. Just if you stamp on it, thank you very much. Now, I have just one more experiment. I have just two more experiments, and we're done. This here contains this is a balloon filled with the lightest gas in the universe. The lightest gas in the universe, as you all know, is hydrogen. And hydrogen is in this balloon, that's why it floats up. And it was discovered in 1797 by the English eccentric Henry Cavendish. Now, I'm going to show that when you set fire to a hydrogen-filled balloon, it burns in air in a moderate way, and it makes a sort of orange flame, and it's nothing spectacular. But then I'm going to finish off with a slightly more special mixture. So I'm just going to light this now. As I said, it's nothing to write home about, but it's rather fun. So hydrogen burning here, pure hydrogen. It makes an orange flame, and it's really nothing that spectacular. I'm just making sure my flammables are out of the way. Here we go. There it is. No, nothing special. Now, I'm going to finish off. My last experiment is going to be to make, now, if I can ask for some sort of rubbish bin, the organizers can organize something bin to throw away all my bits of broken glass and things at the end of this, if we're still here. I'm now going to start off, I'm going to finish off, sorry, I'm getting myself completely tongue-tied and twisted and all around, with the final experiment. Now, this is a very dangerous one, and I don't like doing it, but I think in the interest of science and education, we must allow people to see the truth and nothing but the truth. I'm going to set off 2 balloons which have a mixture of hydrogen and oxygen in them. Now, this is used to propel rockets to the moon. It's one of the most wildly violent combustibles you could possibly imagine in the whole planet. And so one balloon is going to be filled there, and I'm going to link them together by a flash powder, which itself could propel a rocket to the moon. So we're now dealing with very dangerous substances. Now, because this flash powder is so very dangerous, I have to make it on the spot, because if I were to make it earlier, it might accidentally go off and kill me as I'm driving down the road. They spontaneously go off sometimes, these flash powders. So you must excuse me, I must take great care. By the way, it feels very hot here. I think it's from the lights up there. I'm continuously on my guard against having an unfortunate experience. Please excuse me, I'm just moving things out of the way. I'm concerned very much for safety. Here we are. So we've now got this here. I think that'll probably be it. I've got my 2 balloons at the end of our fuse here. I'm going to lay a fuse in there, and then we shall set it off using our mixture of course, my magic medicine man from Shepherd's Bush Market. Excuse me, I'm kicking things all around here. Now, so I'm going to now take some magnesium powder, and which makes one hell of a bright flash. Now, this does produce a bit of smoke, by the way. And it's relatively harmless smoke. It's magnesium oxide, which is not it's not toxic or anything. And I don't want to make too much of it, even though this is a large hall. We don't want to go too large. So if you please excuse me, I've got to concentrate while I do this, because I don't want to do something wrong. So the trick is, you should never ever, or you should have to take extremely great care when mixing metal powders with oxidizing agents, because they are known to spontaneously ignite and go flash and kill you. So I'm taking extreme care when I do this. I'm just mixing together, here we are, some potassium chlorate with magnesium powder. It's a sort of a cookery recipe. I know it works reasonably well, and I'm concerned, as I said, this will make a large cloud of white smoke and a blinding flash, and hopefully there will be a 2 loud bangs at the end, which is what the whole object of the exercise is. Now, it doesn't always work, and I'm just going to lay them along here. You'll see, don't worry about it if you can't see it now. By gum, you'll see it when it's light. You'll see it'll be there. Now, as I said, I'm not sure whether it's that bright, but look, that's it roughly. This is my final stand, and what I'm going to do is I'm going to use my delayed action fuse powder, which consists of potassium permanganate, which I have somewhere in one of my bottles back here. Please excuse me. I have temporarily put it over here to keep it out of harm's way. Et voila, here we are. And this is the final experiment, as I said. I'm going to do a blinding flash. As I said, I can't guarantee whether it will work, but I always keep fingers crossed, and just in case it doesn't work, I'll light the balloons in any case afterwards. So let's put the glycerine on, and then I will and then we'll sort of pretend we're waiting for the battle cry. I'm going to play a little tune while it's all brewing up. As Julian told you, I'm a scoutmaster, so I have to play bugles in the morning. First thing in the morning, we have to wake people up, you see. So that's where I learned to play the bugles in the scouts, you see. So there we are. Here we go. We shall put the bugle to good use this evening. So it's the final battle cry of our splendid evening. We're all lost this evening. And right, there it goes. Now I'm going to start. Ladies and gentlemen, thank you very much indeed. Thank you. Thank you very much indeed. Before we just burn away, thank you very much. Thank you. Please, everything is in order. Thank you very much. Fire extinguisher. Here we go. Thank you very much indeed. I hope I've made my case for the science of chemistry. I bow humbly. Thank you very much indeed. Thank you very much indeed. Thank you so much, and I wish you all a pleasant evening.